Okay, hello everybody. Today we changed the order of the workshops around a little bit, so hopefully that's not a problem for anyone. We will still be covering autoencoders next week, but this week we're going to be taking a look at convolutional neural networks first. Decided to change it because a lot of the autoencoders use convolutional neural networks, at least when they're working with images. So rather than hand waving away that part of it as magic, I figured we could just talk about the convolutional neural networks first. So you'll see in the chat, I have dropped a link to the Wikipedia or the wiki entry that we're going to be talking about today in the first half of the workshop. And then we will be moving on to a Jupyter Notebook example where I have implemented a CNN from scratch. And then we're also going to take a look at, rather than having to train your own CNNs for your task, just downloading a pre-trained model, which has already been trained with, potentially hundreds of millions of parameters, which is a very time-consuming process. So instead, you just download one of those that are already trained and then apply it to your task instead. But of course, first, we're going to talk about convolutional neural networks, and these are very tightly coupled with computer vision. Let me just make sure that yeah, please let me know at this point if you cannot hear me or are there any problems, but looks like we're good. Looks like we're good.
Can you increase the font, please?
Yes, absolutely. Let me change around some of the extra stuff I have. Okay, how is that if we're looking at something like this?
Yeah, thank you.
Okay. And I will make this window a little smaller so I can still see your questions. Okay. Okay, so when we're talking about convolutional neural networks, it's also just generally these came about for computer vision tasks. So we might as well talk about a couple of those first to give you an idea of where you might want to actually use one of these. So computer vision tasks, it's a very, very broad field within machine learning and artificial intelligence. Basically, any sort of data that you have that works with images or things that can be sort of broken into these discrete parts, you can use with a convolutional neural network. So for example, one of the things we might want to do is do a semantic segmentation. So pixel-wise, we are curious, is this pixel, does it belong to, say, some grass, or is it actually a pixel that's a part of this cat? Is it the tree, or is it some sky in the background? So that's a pixel-wise semantic segmentation labeling step. Another thing is maybe if you don't care about that really fine-grained boundary, and all you want to know is, okay, I just want to detect this object in the image, and then assign some sort of bounding box that tells me the object is inside here, and also what is the class of this object. So you can see here, we just have this, this cat. We have a bounding box that completely encapsulates it, and also it's given us the classification. You can extend that to, we don't want to do this just for one single class inside of our object. We want to be able to detect all of these different objects. So in object detection, we can have any number of objects detected inside of the frame. So in this instance, picking up 2 dogs and a cat, and it's generating the labels and multiple bounding boxes for us. And then in instance segmentation, we can say we have these semantically identical instances that we've determined. So we have 2 dogs, and we actually want to be able to say, okay, this is dog number 1, this is dog number 2. How many instances do I have? So that's something like, so I work with plant data in a point cloud context, but we use methods that are somewhat similar to convolutional neural networks. And another instance would be, we're looking at this point cloud of a plant, and we're trying to figure out, okay, this is leaf number 1, this is leaf number 2. What is the relationship between this leaf and like basically which point corresponds to which leaf? There's so many other things you can do. You can do pose recognition. So a very, very classic one would be trying to estimate the pose of somebody's head, which can give you information about what they're looking at in a scene. Pose recognition for your entire body, which leads into activity recognition. If you have some series of frames in an image, you can, by trying to do multiple pose recognitions, figure out what is the activity that they're doing, like running, walking, jumping jacks, etc. You can imagine how that might be useful in, for example, a context in autonomous driving, where you are interested in what the the people around a car are doing, if they're standing versus they're walking in the direction in which they're walking. Very helpful information when you're trying to navigate a scene. Okay, that's enough about like general computer vision tasks. Now we're actually going to talk about, okay, well, what is a convolutional neural network and why do I need this? You know, we've talked about fully connected neural networks. So how is this different from that and why is it interesting? So first off, I'll talk about images. I'm sure that everybody here is pretty familiar with like what an image looks like, but generally we're just going to talk about RGB images. There are many different types, but so for RGB, we have some number of pixels arranged in a grid, which has some height and some width. And for every single pixel, it's actually composed of 3 separate values, which are the red, green, and blue values, which are basically chosen because the types of cones, the type of color that our eyes can perceive is red, green, and blue. So you can think of this as having some sort of 3-dimensional shape where it has a height, a width, and then a depth of 3. It's just this really thin, like rectangular feature. So we had seen in the fully connected neural network case that we have this MNIST data set where we were able to take this neural network and classify digits. So very simply, the way that we were doing that is you have to take this image, which has, you know, inherently, in this case, 2-dimensional structure because we're just using grayscale values. But to feed it into the neural network, what we had to do was take that image and then just like unspool it so it's this 1-dimensional vector. And then once we have that 1-dimensional vector, it's ready to go into that first layer and get fed through this network. This is maybe not advantageous. And a very, very simple example would be, imagine this is instead of having a full digit, let's just say we have this dot that's appearing in one spot in our image. So you have either high or low, 1 or 0. And here you can see that that dot moving to the right one actually changes the position in that input vector. And because this is a fully connected neural network, just moving that high level over by 1 position means that it's interacting with a completely different set of weights. So whereas at the very top left, it's interacting with 1 set of weights as it's getting fed into this first layer. If you move it down by 1, it's just a completely different set of weights. So if what you were trying to do, for example, was learn what a 1 looks like in that MNIST data set, just moving the 1 over by 1 position on all of them is a completely different, it looks like a completely different input image to MNIST. And, you know, a fully connected neural network, because these images are very small, is capable of learning that. But we would prefer, as we start to move into larger and larger images, that we don't have this problem, that our network is capable of recognizing that structure no matter where it's appearing. And then like a kind of larger example of that would be if we have, let's go back to our image of this cat up here. We want that whatever network to figure out this is an image of a cat, no matter where the cat is appearing. So whether it's like up, it has its face up here and its body is out this way, or perhaps it's flipped and its face is down here and its body is this way. We want some sort of structure that can just detect it no matter where it occurs in the image. Okay. And that property that we're looking for is called translation invariance. Basically that it's going to give you the same output no matter the fact that you're translating the input around in this image space. And that's what convolution does for us. So before we talk about specifically what convolution is, I just wanted to give a sort of broad overview of the architecture itself. So this is a pretty simple example of a CNN architecture where you have some input image and it's getting fed through the successive layers of, you know, we do convolution, we do an activation off of that, and then we pool all of these activations. And we're doing that, you know, potentially multiple times until we get down to this reduced space. So we have this really big image and we're just trying to extract semantic information out of it until we get down to this smaller representation where rather than having pixel by pixel, maybe we figured out, oh, there's like a big block of this exact same color. So I'm just going to describe that very simply. And once you get down to that reduced representation, that's when we can finally feed it into a fully connected neural network. So we can see here that this network is doing classification, and before we put it into the fully connected neural network, we're doing this flattening step where we take our higher level semantic information that this convolutional neural network is extracting for us, and we are turning it into that one-dimensional vector. Anything else interesting here? And you can see that we're actually using just the rectified linear unit as the activation as well. Very simple, but it was actually a very big step in convolutional neural networks to start applying it here. Okay, so with that overview, we have these convolutional layers and then these pooling layers. What are both of those actually doing, and how is that helping us extract this high-level semantic information? Well, convolution is not that complicated. The math looks kind of scary when you learn it, especially in a continuous domain. But the idea is really here that we're just trying to learn some filter. And here you have this example of a 3x3 filter. And we set these filter values. In this case, we're just doing a binary 1 or 0. And then we're going to pass that over the image. So you can see that, like, for example, this would be our filter being passed over this underlying image. And the idea is that anywhere that the underlying image looks very similar to the filter, you take this inner product between your filter and the image, and it's going to give you a high response in places where your image looks a lot like that filter. And it's going to give you a low response elsewhere. So just taking a quick look at the math on this, for example, we have this filter, it's doing this inner product with this part of the image, and you can see that anywhere it has a 1, where the filter has a 1, it is contributing to the final sum. So we have this, and this one, as well as this one, and that is our activation of 4. You can see the maximum activation here would be 5. So that would be the image looks as close to the filter as possible in that location. So you can see over here that we would only have like this one hitting this one, so we get this activation of 1. So that would be a low activation. In this area, the image does not look very much like the filter. So with convolution, we're just taking this, we slide it over the entire image. This is just a one-dimensional example. For our RGB images, we're actually doing this kind of on all 3 of the layers at the same time and just sliding it around to see, okay, where is there a feature that looks like this? And then once you have that, basically that measure of similarity to the filter, it's going to feed it through that activation function. And we'll get the output of the convolutional layer from that. So before, this actually comes from, this idea of convolution was used in computer vision before neural networks were really as powerful as they are today. So what you used to do is you would basically hand design your own filters. So you would say, I think that maybe this task would benefit from having like a 3x3 kernel or like a 16x16 or something. And I'm just going to try and find edges at various angles. And I'm going to try and find dots, like really, really basic stuff. And then using those features, I'm going to try to build sophisticated models that are going to maybe match areas that have similar features between 2 different images. So that'd be like key point matching. So I have like a picture of one object from 2 angles. I'm trying to figure out, okay, in this image, this is where the correspondence is. This is the same point between the 2 images. And convolutional neural networks use the same thing, but you basically parameterize it so that you learn the filters as well. So instead of having to hand design these filters to try and pick up edges, you just initialize it to random noise, as we've seen, and then you let it train, and you can just do the backpropagation with the loss function, as we've seen before. And then interestingly, this is a 2002, I think this is a 2012 paper where convolutional neural networks were used on this ImageNet dataset, which is 1,000 classification. In 2012, it came out and it beat state of the art at that point by like 16% accuracy, I believe. And it really kicked off like computer vision using convolutional neural networks, like as it's used today. But what they noticed when they actually looked at all of the filters that it was learning is that a lot of the filters it learns kind of correspond to what we had been trying to hand design. So you have these like lines and things that are appearing at various angles. You can even have like it's trying to pick up dots where the underlying color kind of matches what this filter is, and things like that. Not all of them are really human interpretable though. Like I couldn't really tell you what it's looking for here. Maybe this is trying to pick up some sort of underlying texture. But like it is picking up kind of these very, very basic features, like these filter banks that used to be designed by hand. So there's one more thing. So that's like the basic idea behind convolution. If there are any questions on it now, please feel free to ask. But that would be in your network when you're implementing convolutional layers. There's two hyperparameters that we've already talked about that directly relate to the kernel, which would be you have to tell it how big you want the kernel to be, whether it's a very, very tiny kernel like 3 by 3 pixels or like 16 by 16, 32 by 32 as it's sweeping over the image. So you have to tell it the size. We also need to tell it basically how it's going to move around the image. So that would be two different hyperparameters here, stride and padding. So all stride is telling it is this is the number, you do the convolution operation here, and then move over by some number of pixels. So in this example, we can see that the stride is 2. It does the convolution with the image in this location, moves over by these 2 pixels, and does convolution here. And then we can also specify to add some padding around the outside of the image. So commonly you would do 0 padding, and it's just adding another layer of basically a black pixel because 0, 0, 0 and your RGB is black. So you can pad with a couple of pixels, and instead of starting up here in the upper left corner of your image, you would just come out to the actual start of your padded image. So in this case, you have a padding of 1 pixel around. And this can be helpful for if you're looking for a line and you have some sort of line that gets kind of truncated or it's maybe only half on the image, adding some 0 padding will let you kind of step outside of the image and try and find that feature. So that's, in a nutshell, what convolution is doing. It's just trying to find underlying parts of the image that look like the filter that it's learned. And then once we've done that, we feed it through some sort of pooling layer. So you're trying to learn all of these different small features and then extract like, okay, I found this or I didn't find this. And that's still a pretty high dimension. We want to be trying to get the network to only find the most salient features. So rather than capturing all possible information, we try to get it to capture useful information only. And pooling helps with that. So all pooling does is it's kind of similar to convolution in that it's looking at underlying patches. But what it's doing is it's saying, okay, I have some underlying patch with all of these activations from the filters. I'm only going to preserve some of that information. And you can preserve either just the maximum activation. So in this case, you have some filter that in these 4 different spots had these activations, and you would say, well, I only want to know, did it find it in this area? So I'm going to just take the maximum. So that would be max pooling here. You can see that it's just taking 20 from this red square area. It's taking 30 from this yellow one, and so on. Another thing you can do, although this is used much less, is average pooling, where it's just looking at the average activation. Intuitively, I think this works. Max pooling tends to work better and is used much, much more widely than average pooling because it's more helpful to say, did I find this or didn't I find this versus here's about how much I found it in this entire area, which means that you could be kind of down tuning this really strong response if there's not another strong response nearby. And this one doesn't have any learnable parameters. This is just, it's doing maximum or average. There's nothing to learn in that location. Okay. So both of these things together, these convolutional, so the kernels that you learn basically allow you to learn one kernel that is then shared across the entire image. So I'll take you through some of the numbers for an AlexNet architecture, which is another pretty early convolutional neural network, and compare how large that is to a fully connected network. So AlexNet, these input images that it was capable of running are 227 pixels square RGB images. And it immediately feeds this into a convolutional layer, which is 55 by 55 by 96. And here 96 is the number of filters that it's passing over this image. So it passes these 96 filters over, and it's just getting all the way down to 55 by 55 for each. So every filter itself, which is the actual thing that we need to learn, is only 11 by 11 by 3. So you have to learn 364 parameters per filter, and that's only about 35,000 parameters for this entire layer. If you did this with a fully connected neural network instead, you actually have to learn about 44 billion parameters just for this one layer, because it's fully connected. So every single input in the image has to go out to that 290,000 output neurons, which is just like, it's massive. It's untenable, and you would need multiple layers like this to start extracting actually interesting information. And like 227 square is not a large image at all. So it's not tenable, and that's one of the reasons the convolutional neural networks are so powerful, that it has these filters that are useful everywhere, and we only have to learn once. And you'll note that these filters are, again, because you just have the same filter that's just getting swept across the entire image, we've achieved our goal of translation invariance. This filter is going to detect what it's looking for no matter where it is, because it's being applied across the image. We also have, I just wanted to show here some of the activations that are coming out of one of these layers to kind of give you some intuition for like what's happening as we are going further and further into this network. So we have here 2 convolutional layers before we do a max pool, another 2 convolutional layers before the max pool, and then one more time. And we're just trying to predict the class. So we have this last layer is going into some fully connected network that's doing the class prediction for us. And you can see that like the activations that are coming out of this very first one still looks mostly like a car. Like we haven't lost that much information yet, and you can kind of tell what it's paying attention to. So like in this one, you can see like it kind of looks like it's detected this hood. That's a very bright spot. Versus down here, oh, it's like found this like shadow around the base of the car. And so on and so forth. But then as we are kind of going further and further into the network, you can see that we're losing dimensionality. The pixels, like each pixel is a lot larger, and it no longer looks very much like a car. So we're dropping this information, like specifically these tiny spatial details, to try and build it into, okay, I have maybe one edge, and then if I find maybe these 2 edges, that's it turns into a corner, and then maybe if it finds a couple corners in this one location, it can say that is this larger shape, a square, a rectangle, something like that. So it's progressively building up these tiny features into something that's semantically interesting. Like, okay, we took all of these tiny features and we figured out this is a wheel, and I find wheels on cars. So while it's basically dropping information that we don't need, it's because it is trying to find these like high-level semantic features, which are a lower dimension, that describe the car versus everything else in the data set. Yeah, I think that's also that's a pretty common way that neural networks like are intended to work, extracting useful information about your data and discarding things that are not interesting. Okay. And to just hammer this home a little further, this is the VGG16 architecture, 16 because it has 16 convolutional layers. And this is from, I think it's the visual geometry group in Oxford or Cambridge. Anyway, so this model is a few years old at this point, I believe. It works on the ImageNet visual database, so that's 1,000 classes, and it's capable of achieving 92.7% accuracy. This is like, since then, this has been pushed to like 99% accuracy, but it's required massive amounts more parameters and layers and things like that. So really the interesting thing here is it's a very like simple architecture, but it's still very effective in what it's attempting to do. Like it hits 92% accuracy. with just 16 layers. So these are very, very powerful in their use on images. And again, just want to emphasize we're sort of forcing all of our information to go through this bottleneck here, where we force it to only pick out the most salient features and combine them in the most interesting ways until you get down to this very, very small representation of the image. We go from this, I think this would be 224 by 224 by 3. No, I think the initial images are larger, excuse me. But you go from this very large image to something that is only 7 by 7 by 512 by progressively applying a lot of filters to it. And then this pretty simple fully connected layer can figure out what the class is out of 1,000 classes. Okay. So from here, if there are not any questions, we can jump into the Jupyter Notebook. And I'll send the link for that as well. Okay, so hopefully everybody can get to this Jupyter Notebook okay. Just let me know in the chat. We can help you out if you're having any problems with it. Right now, I would not recommend running everything because I've already run everything, and all of the output that we're going to be interested in is already in these code cells, the code blocks. I highly recommend playing with this later, but one thing to note is this Jupyter Notebook is actually, it requires access to a GPU to train these models. As we start to get into these models that have more parameters, it's just going to take too long for it to run on the CPU. So it will just run significantly slower. If you do want to play with it later and sort of change around some of the parameters, maybe add in another layer or two and see how far you can push the accuracy on this, highly recommended. It was taking me about 15-20 minutes to train using one of their GPUs. So we should be able to do it from Google Colab's free tier, assuming that they have excess GPUs on that day. But okay, so the first example we're going to go through is actually, we're going to look at just training a CNN completely from scratch. And the data that we have trained this on is called CFAR10, which is a data set that has 10 classes, very, very widely used in the literature. There's so many papers use this data set in the vision space. So you can see the images are really tiny. These are 32 by 32 color images, so 32 by 32 by 3 color channels. And we just need to learn to classify them into one of these 10 classes. So what we're going to do is we're going to train a model and then evaluating it using top 3 accuracy. So top 3 just means that if the model outputs the correct class as one of the top 3 predictions, so you have these logits, which are like the unnormalized probabilities that it thinks each class are. So if it's in the top 3 of those, then we consider that a success. And if not, that is a failure. So here we're going to be using PyTorch and Torch Vision. Actually, they just supply CFAR10 as one of their data sets, along with some others if you wanted to play with a few more data sets after this one. And we'll also be using Lightning, which is a wrapper for PyTorch that makes it easier to train your models and organize your code. So the first thing we just need to do here is download the CFAR10 dataset, and they have this very nice function where you just tell it, I would like you to download this into my current working directory. You tell it download the train or the test split, so train equals true or train equals false. Here we tell it, okay, when you download it and put it and actually open that data for me to use this transformation. And all this transformation is doing is taking it from the original type, which I believe is a PIL image, but I'm not 100% sure. But we're just saying, please take this and turn this into a tensor. And a tensor is what PyTorch is expecting. It's the values that it needs to feed into the model. So this just automatically tells it, please run it through this transformation first. And we allow it to download because we do not have it locally. So once we have our data set, then we transition into loading it in a data loader. And it's very simple. All this does is it takes your data set, which is just, 50, let's say 50,000 images, and it's going to wrap it in an iterator. So what that will do is once you tell it the batch size, in this case, 256 images, every time we call it, it will give us an entire batch of 256 images. And then we can also ask it to shuffle the images or not. So with training, you do want to shuffle them. So it will, at the beginning of every epoch of training, reshuffle all of these and then serve them out in the 256 batch size. And then similarly for the test batch size, I just give it 8 because we'll be doing some visualizations with it later, and 256 is too many to look at. Okay. Okay, so the next bit is, this is the actual convolutional neural network architecture. So here we just organize this into a Lightning module, and Lightning is going to handle some of the training details for us. But the first thing you need to do is tell it, here's the actual, all of the layers and things, how they're organized, and what their sizes are. So that's what's happening in this block of code here. This is a very, very simple CNN. So it just has one convolutional network followed by a pool, a second convolutional network followed by a pool, and then we flatten it and we put it into a 2-layer fully connected neural network. And then here, this softmax is going to take the output of the fully connected neural network and turn it into a log likelihood for our loss function. I'm also defining here, they just have this nice utility class called accuracy, and you can tell it, okay, this is a multi-class classification task because we have 10 classes we're trying to classify in. So we tell it how many, and then we can also just say, and it counts if it's in the top 3. So this is very simple. It just wraps this up for us. We don't have to write any of the code to calculate the accuracy. So we store that and we'll be using it in some of the methods. Now, PyTorch also wants, or excuse me, Lightning also wants the forward pass, and the forward pass here is very simple. We get given an image as a tensor, and we just pass it through our layers, and we return the output of the entire network. And then just quickly, we'll look at the training step. All the training step is doing is calculating the loss. So we get this batch. We pass it to our loss function, which passes it forward through our network, calculates the loss function, and returns it. And then all training step does is we're going to log it and then return the loss itself. Validation is very similar, where it needs to actually calculate the loss by passing it forward, and we're just also logging an accuracy at that point. So all we have, the only difference between these two is we calculate an accuracy using the logits, and then save that as well. And finally, Lightning, you don't have to configure an optimizer, but we do in this case because it will speed up training and generally make it more stable. So we are going to use like a very, very common optimizing scheme called Atom. And the only thing we're going to do here is just give it a learning rate. Very common to use 0.001 as your learning rate as well. And we tell it, you're going to be the learning rate you want to apply, and you're going to monitor it by looking at the validation loss at every step. And that's all it needs. All the Lightning module needs is the forward pass. It doesn't even need the validation step or the training step, or excuse me, the test step. It just wants the forward pass. You have to tell it what loss function you're using and how to train, and that's it. So here, we're just instantiating a member, our convolutional neural network. And then we set up a trainer, which is going to do all of these training steps for us. So rather than having to do these for loops where we are telling it how to go through the epochs and doing all of this stuff ourselves, we just say it's going to handle that for us. So we're telling it, okay, you can use the GPU for this, use one GPU, and we give it this extra parameter that just says, and you can stop if you have not seen any improvement in our validation loss in 3 epochs. So that's it. You're looking at the validation loss, and after 3 epochs, if you have not improved, you can stop training. And then it's as simple as calling trainer.fit. So we give it our model, and then we give it the data, the train loader and the validation loader. And it will start training for us. It prints out some useful information like, okay, we're using the GPU. That's all this says. that there is one available and that we used it. You can see that I didn't specify the max number of epochs that it's supposed to go through. So it just automatically says 1000, but we're not worried about that because we did tell it that it could stop early. And we can see that it also prints out some useful information about our model. One thing I maybe don't like about the way that they set this up is that if you do put all of your layers into this sequential wrapper, which just means go through all of these layers sequentially, it does not, in this little overview, tell you what's inside of it. But it will tell you this is the number of trainable parameters that we have in this layer. You can see it's just printing out all the members in the class that we have given it. So it also shows you, okay, you have some accuracy. So this particular run that I did, it ran in 36 epochs before finishing. And here I am using TensorBoard to look at all of the different things that we logged. This also shows the epochs for some reason, which is not useful. Okay, so let's take a look at what it was doing when it was training. So we were logging the training loss, so we can see that generally the training loss was decreasing. Because we're shuffling the data and we're using this stochastic gradient descent, it's not this nice smooth curve. You'll have some variance in terms of the gradient and the loss as you're moving around this optimization space, but it is decreasing. Now, if we look at the validation loss, we can see that the validation loss was also decreasing pretty much the whole time, and then looks like it has bottomed out here at the bottom. And then looking at the accuracy, we can see that we started out and very quickly got to about 74% accuracy before maxing out at just above 80%. So this can be very helpful. What it does is it just saves all of these different logs into a new folder called lightning logs. So if you want to run multiple trials, say you're trying to change, you're tweaking the architecture or you're changing some other hyperparameter like the learning rate that you're giving to Atom or other things like this, it will save all of these logs in like version 0, version 1, version 2, and you can directly compare like what was happening with the loss or what's happening with the accuracy and things like that. And it will actually plot all of these on the same plot for you. So it would have like, say version 0, it's like purple and it shows a purple line on this plot as well. So it's just like a very, very nice thing to be able to use when you're training your models. Okay. In this next section, we're actually going to take a look at what the predictions what predictions it's giving to us. So I defined some functions here, which are just going to be helpful in terms of showing the array or showing the image. So you can see here that imshow is just using, we're converting to NumPy and then passing that into matplotlib. And here we are taking some random, this should be test images, excuse me. So we take some random test images. And we do that, it's just you're getting this generator from the test loader and then iterating through it. And these are the ground truth classes in the order that they appear in our data set. So a 0 corresponds to plain, etc. We will just show those images. More interesting though, we're going to actually run it through our model and see what it thinks the image is. So here to run inference, we have our trained CNN. So we're getting the logits out of the end of it, which is the probabilities basically of what it thinks probability for each class. We are calculating the accuracy again using this accuracy module with our multi-class task, and saving it in this test accuracy variable. For the predictions, we're grabbing from our logits the top 3 of them. And then in this area, all we're doing is for every one of the images, we take these, basically the index, which is like 0, 1, 2, and we're just grabbing a string out of that. So for 0, we would go grab plain. For 2, we would grab bird, etc. And then here I just have this little like string formatting code where if the prediction is correct, that is the true class is one of our 3 classes, we're just going to format that green and print it out. Otherwise, we format it red, and what we're going to show instead is the top thing that it thinks it was. So here's our images that we ran through our model. So you can see that we have this like truck, the horse, the plane. If you look at this red means that it predicted this incorrectly. And you can see that for this one, it's got this horse and it thought that this was a frog. It thinks that this one is a horse and this one is a bird. So it's definitely not perfect. It's a very small CNN, and I'm pretty sure that like very large architectures these days can hit like 99% top 1 classification on CFAR10. But for a toy model that's very quick to train, this is doing pretty well. And then if you come back to run this later and you run through this code, I don't have a seed set, so you might see these change and the accuracy will change because if you're only drawing 10 samples, you can have a pretty high variance in accuracy that's not what it would show you on the entire test set. Okay. And that is it for our training a CNN from scratch part of this tutorial. If there are any other questions, please feel free to ask them now before I move on to the pre-trained CNN part. Okay. Okay. So I hope that you have some fun like playing around with that CNN. But if you just want to get something up and running that's going to work for your specific task, I would not really recommend that you start with like training your own CNN unless you're trying to push something about like push forward the research in like the area of CNNs or on your specific task. If you just need like, okay, I just need a model that's already trained and what it's going to do is just detect something in this image for me, you should start with a pre-trained model. So there are a lot of foundation models at this point that you can just download. They have millions of parameters. They've already been trained. So all of the really intensive GPU work for training them has been completely done. And these are just available for your use. So these are either a good benchmark for what you would want to be able to achieve or probably just all that you need. So what we'll do here is basically first just download the model. In this case, we're going to be downloading a faster RCNN model from PyTorch as well, actually. And faster RCNN is doing object detection. And then we're just going to set up a function that will pre-process the images for us. So download an image to this local Google Colab setup, and then get it ready to feed into the model. So the function to perform detection is just going to take the model, run our new pre-processed image through it, and then we're going to just write another function that says, given these object detections, I'm going to draw them onto the original image and then show you the result. Okay, so here, just downloading all of these images. We have 2 that are just like apples. Actually can run this part of it, and that will be interesting to watch. Okay, so we just got these 4 images that we can use for testing. Here, in this location, we are downloading this model. It's the ResNet 50 faster RCNN. It won't take that long to download. And in this case, because we're using PyTorch and not PyTorch Lightning, you need to put the model into evaluation mode, which just says, don't do any backpropagation, don't calculate the loss. I just want to use this for inference. So I will give you an image and you will give me the object detection. And similarly, we just have this transformation, which says for the image, turn it into a tensor that our model can consume. Okay. So this function here is going to perform the object detection. So we pass in the model, pass in an image, and then we're going to give it a threshold of 50%. So this is pretty straightforward, just your input image, you transform it, and we're going to remove an extra dimension that's not needed. Do the inference. So no grad is kind of the same as evaluation. We tell it don't calculate any gradients. So we get this prediction. And then for the prediction, we have boxes, scores, and labels. So it's telling you where it is. The score is how confident it is. And then the label is the class that's inside of that box. So we're using our threshold here to say, I only want you to show me the object detections that have a score of greater than 50%. So basically, I don't want to see stuff that's like, maybe you're only 10% confident that there's something here. I only want to look at 50% and more. Okay, this function here is actually going to draw a bounding box onto the image. So up here, we get these boxes, which are basically like, you can just get a max X coordinate, max Y coordinate, and then the minimums, and it just determines this box on the image for you. So we're using this library here, just called image draw, in order to draw a rectangle that is the bounding box on the image. And then we're also adding some text here that says, here's what the label is, and here's what the score for this one is. Okay. And then visualize results. We've gotten these boxes. So this image with boxes, it's already drawn onto it, and then just display it. So first one I ran through here is a picture of my cat. And you can see that the bounding box managed to capture basically all of her body. Just missed an ear here. It is showing, this is a very, very large image. So it's showing this text, but it's pretty small for the label and the score. I'll also go ahead and run it on one of our other examples, which should not take as long. And what the faster RCNN here is doing is it does this pass of the entire image where it generates proposal bounding boxes and then does a second one inside of that to say, and this is what the classification is. So for this image, you can see that this is kind of interesting behavior where it does find this knife, which it says is a label 40. So if we were to look it up in however many classes it was trained on, we could double check that this is actually correct. And you can see that it's also getting these individual apples. So it does have one for pretty much every apple on the board, but then it has this additional bounding box that's capturing, it's saying, okay, everything in here is also just one apple. So it is getting a little, and that's only 73% thresholding. So it's like fairly confident that it has found an apple. One thing you can do here, if you are using this for your tasking and you're getting a bunch of like spurious object detections, or it's detecting the same thing multiple times, you can just kind of play around with the threshold and just turn it up until it seems to be working better. So for this one, I might try and make the threshold like 80%, because it looks like most of the object detections are 80% and above, except for this one, which is like 70. But that's kind of like you would run it on a decent amount of your data and then just like try to find some threshold that's going to work well enough for what you're attempting to do. Okay, and that is the end of the material that we have for convolutional neural networks. So I'm very happy to stick around and answer some questions if anybody has any. Otherwise, thank you for your attention.